And all of these functions are defined as some sort of relationship with f and g, or maybe just one of those. And I've also given you a table of values of f and g at certain x values and the derivatives of f and g at certain x values. Again, the AP exam kind of uses these type of questions to test students' knowledge of like, do you recognize when to use a certain rule and can you use it correctly? There's a lot more of these on that homework 7 that I've been halfway alluding to the past few days as well. But I did want to kind of open up class looking at how we do derivatives when we don't actually know the function and just using the function notation. And then we'll finish up with our chain rule stuff. So looking at these problems, I have J, M, T, and U as functions. So this first one, for example, is asking me to find J prime of 0. We can see that J of x is defined as f of x plus g of x. So if I wanted to find J prime of 0, I would want to find J prime of x first. Well, looking at J, we know that when we have multiple terms of a function, we just take the derivative of each part. So if J is f plus g, J prime is just going to be f prime plus g prime. And then once we find the derivative, we can find it at the value we're looking for. So I'm trying to find J prime of 0. That's going to be the same thing as f prime of 0 plus g prime of 0. And I can use the chart provided to evaluate that. So I don't know what f is. I don't know what f prime actually is. But I do know that f prime of 0 is -2. And I know that g prime of 0 happens to be 0. So what is this j prime of 0? J prime of 0 ends up being -2. And depending on the function, sometimes different rules are involved. For example, the second one, I'm asking you to find m prime of 2. If I'm looking to find m prime of 2, I of course first need to find what m prime of x is. M of x is f of x times g of x, so we actually have to use the product rule. So we don't know what these functions are, but we do know the format of the product rule. And the product rule states we take one of the factors and multiply it by the derivative of the other, and then plus we switch which one we've taken the derivative of, bringing over the original one that we took the derivative of the first time. So again, if I wanted to find the derivative at 2, the derivative at 2 would be whatever f of 2 is times the g prime of 2 plus f prime of 2 times g of 2. And again, I can use the table for this. F of 2 is 4. G prime of 2 is -4 plus f prime of 2, which is 0. So it doesn't really matter what g of 2 is, but I'll fill it in. G of 2 is -4. So what is m prime of 2? -16. Those are ones that you could have done technically before we had our quiz. Those are just using like the product rule and taking the derivative of each term. Could have also done one that was like defined as f divided by g or something, so you had to do the quotient rule. These other two are ones that we couldn't do without what we learned yesterday. So number 3 is asking you to find t prime of -2. Well, we do need to find t prime first. Looking at t, though, is defined as f of x squared. So this is a clue that we're using the chain rule, even though we don't know what f is. We know that x squared is inside of f, and we use the chain rule whenever we have a function inside of another function. So if I want to find the derivative of t, we take the derivative of the outside first, which is f. By the chain rule, the inside stays the same, and the inside was x squared. Then we multiply it by the derivative of the inside, which is just 2 times x. So when I want to finish this problem out, we're asking to find t prime of -2. So that's the same thing as saying f prime of, well, x squared is on the inside, -2 squared is 4 times 2 times plugging in -2 for x. F prime of 4 is 4. So we end up with 4 times a negative 4. T prime of negative 2 is negative 16. I do want to pause right now to see if anyone has any questions, particularly on that number 3, as it does use what we did yesterday with the chain rule. All right, and then I'll just quickly finish it up then. So that fourth one, we are looking for u prime. And again, I want us to recognize that if u is defined as f of x squared, this time the squared is the outside function, so the 2 comes down in front. The inside remains unchanged. The new exponent is now the first power, so that was with the power rule, times the derivative of the inside. The derivative of the inside is f prime of x. Evaluating this, I'm finding u prime of 4, and we have 2 times f of 4 times f prime of 4. 2 times f of 4 is 0. F prime of 4 doesn't really matter, but it's a 4. So we get that u prime of 4 is equal to 0. Realize we can interpret some things here, so I don't know at all what this function u looks like. I definitely don't know what the function, whatever f of x squared looks like. But I know that now for this function u, since the derivative is equal to 0 at 4, I do know that this graph does have a horizontal tangent at x is equal to 4, and that's just to make some connections with some other things that we've looked at this unit. Questions, concerns, or things I can clarify about any of those 4? All right, so yesterday we did talk about the chain rule. And I said the chain rule is basically a rule that can show up no matter what. It's going to be a rule that can show up with all the rules we have learned and all the rules that we will learn. And that does include things like the product and the quotient rule. So some of you might have already seen an example. If you were working on the homework last night, you probably got to some examples that involved the quotient and product rule with the chain rule at the same time. This would be an example that uses a product and the chain rule. I know it's the product rule because I have 2 things being multiplied and they both have x in it. So I have this 6x to the 4th, and then I also have this x squared minus x to the 9th. And so I am using the product rule. The second one, since I have something raised to the 9th power, is where I'm going to have to use the chain rule. So taking the derivative, we just have to think about all of our rules happening together at once. So I am finding y prime. So I have the first, and I'll go back and highlight it when I finish. The first times the derivative of the second. This is where the chain rule comes into play. So it's 9, new exponent is 8. Inside stays the same, times chain rule, the derivative of the inside, plus the derivative of the other one now. So I'm going to take the derivative of the 6x to the 4th. 4 comes down in front, giving me 24x to the 3rd power times the original of that second term. So we can see that we have used the product rule. And then we also had to use the chain rule when I took the derivative of the second part here. Oftentimes when you are doing the product and the chain rule, there are ways to simplify your answer to make it a little bit nicer. For example, if I told you to find horizontal asymptotes on this function, that's a pretty messy function to solve. If I were simplifying this instead of foiling a bunch of stuff out, I would probably actually try factoring it first. So looking at my numbers, I might say, okay, looking at the coefficients, I see 6 goes into both of those, and I can also factor out x cubed. Also, because of the way like derivatives work, I do notice that they both have this x squared minus x in common. How many do they have in common? They have at least an x squared minus x to the 8th in common. So then I could fill in what is left over. I took out the 6, I took out x cubed, leaving 1x left over. I did not touch that 9, so I have a times 9 there. I took out all of the x squared minus x to the 8th power, but I did leave over this 2x minus 1. And then for the second term, after the plus sign in the product rule, again, I took out a 6, leaving a 4. I took out all of the x cubed. I took out 8 x squareds minus x's, leaving one of them left over. And then I can kind of simplify it from the inside outside. So this inside portion right here, that's a 9x times a 2x. So I have this 18x squared minus 9x plus 4x squared minus 4x. And so A simplified, there are some things we can go a little bit further, but I did just want to go at least this far to show us that there are some ways we can simplify these problems. Combining my squareds, 22x squared minus 13x. So that's just some simplifying some algebra. There are some other things I can do, like I could factor out an x again from that third set of factors, and I can even kind of pull out an x to the 8th from that second factor. But I did just want to kind of show you that if you have to do anything with the derivative, we know that it's often easier to simplify these problems first. But what I am focusing on this is, can you use the product and the quotient and the product and the chain rule together to find the derivative?
Is that supposed to be 6x cubed?
Probably. Oh yeah, it helps if I carry down what I did. Yes, thank you, Matthew. Any other questions, or hopefully not corrections?
How far should we simplify if they just
So
ask?
if it's a quiz and it doesn't tell you to simplify it, I would stop like as soon as I take the derivative. Like I know I just finished writing your test for next week, and there's like a page of just find the derivatives, and I put in like bold letters with just like take the derivative and don't simplify. Like save your time, find the derivative, and just move on to the next question. Where you'd be forced to simplify, if say this was like a multiple choice question, you would want to at least simplify it until you can match up the choice that you have. Or if I had a question like find the horizontal tangent line, I would probably go down to at least where I have it stopped at, because I can easily set those 3 factors equal to 0. So it really just depends on like if you have to do anything else with the derivative. If you just have to find it, then I would stop and not worry about simplifying it. Also, because if you like have the correct derivative but simplify it incorrectly, you actually lose points. So sometimes it's better to leave it unsimplified if you can. So one more of combining rules, and I'm actually going to change it from what I distributed out to you, just because I don't like, I mean, it's doable, I just don't like how it looks. So I'm going to make it look prettier. So ignore if you're looking at notes to follow along. I am going to give you a chance to try to find the derivative of this on your own first. I'm going to do all of it squared and just be 2x over the secant of x minus 5. And that 5 is not inside of the secant. So go ahead and see if you can find that derivative for me. And I'll give you a second. I guess you can assume, obviously, since you see that combining rules, you are going to be using more than one. I think it's pretty clear that's going to be the chain rule combined with the quotient rule. Don't worry about simplifying this one. It doesn't really, there's not much you can do when it comes to simplifying. But I'm going to give you a moment to that, and I just have one more slide after this. So there is my answer. So I have the chain rule is and the quotient rule is involved. And when I'm looking at this, I can see that the squared is what's on the outside. So I had to take the derivative of the squared part first. So 2 came down in front. Inside remains exactly the same. New exponent is 1. And then I want to multiply that by the derivative of the inside. And the derivative of the inside we do see is the quotient rule. So I have low d high less high d low. Remember, the derivative of secant is the product of secant and tangent. The 5 went away, of course, because the derivative of a constant is 0. And then draw the line in down below, the bottom squared will go. Not too much you can do to really simplify this. If you were wanting to simplify it, since this is now to the first power, I can kind of drop those parentheses. So I have 2 times 2x, so there's like a 4x up here. Your denominator, you have 1 secant of x minus 5, and then 2 more. So you end up with secant of x minus 5 to the third power in kind of a simplified version. And then this numerator is not going to simplify nicely at all, but we're going to have 2 secant of x minus 10 minus 2x secant of x tangent of x. So not a simplified answer, but we can see that we have 2 rules happening at a time here. We have the chain rule on the outside kind of happening with the quotient rule when we do the derivative of the inside. Questions or concerns about that one?
Is that supposed to be a third power on the bottom?
Yes, because we have this one down here to the first power, and I'm multiplying in the denominator by 1 that's to the second power. So
All right.
Come to the third.
Mr. Brown,
Yes.
that 2 secant of x minus 10, that minus 10 isn't in the secant, right?
Right, that's outside of the secant. If the 5 was inside the secant, I would have written it like this instead, to be clear. But it wasn't like that. Anything else? All right, so then the last slide. Most of you probably don't need to know this because you can figure it out because you're smart. But we talked about like the first derivative and the second derivative. We know how the first derivative is mainly associated with increasing or decreasing, where the second derivative is mainly used for concavity. But when I say find the second derivative, that literally means take the derivative of the first derivative. So if you ever have a problem that's asking you to find the second derivative, you literally find the first derivative and then use the first derivative to find the second derivative. I do often simplify between those steps because we do know that the simpler your answer is, the easier your derivative is going to be. So if I want you to find the second derivative of sine squared of 3x, if it helps you again, you can think of this as the sine of 3x squared. So it is going to be one of those examples where we have to do the double chain rule, 2 chain rule, however you want to think about it. Because if you're looking at this one, we do have the squared on the very outside. Inside the squared is a sine, and inside the sine is a 3x. Making sure we label it correctly, so this is the first derivative of x. So taking my derivative, this 2 is going to come down in front first, the new exponents to the first power. We leave the inside the same because we haven't touched it yet using the chain rule. Multiply it by the derivative of the inside. So the next inside is sine. The derivative of sine is cosine. Again, leaving the inside the same. Then chain rule again. The derivative of 3x is just 3. So that is the first derivative. Again, before I would go and find the second derivative, I would simplify that. Not too much you can do to simplify it, except now the first derivative is going to be, I have some coefficients. 2 times 3 is going to give me 6. And then we have sine to the first power of 3x and cosine to the first power of 3x. So this would be my first derivative. So now if I want to find my second derivative, I just need to find the derivative of the first. Well, looking at this one, we do notice that I have a sine with an x in it and a cosine with an x in it. So that is going to be our clue that we are using the product rule here. Doesn't matter which one you kind of attach that 6 to. I'm going to think of this as 6 sine of 3x times the cosine of 3x. So we are going to have to use the product rule and the chain rule at the same time, because again, we still have that 3x inside of both sine and cosine. So now this is the second derivative. So I have the first times the derivative of the second. Remember, the derivative of cosine is negative sine. Inside stays the same. Multiply that by the derivative of the inside. And then plus, I have the second, and I want to multiply that by the derivative of the first. So 6 is the coefficient that came across. The derivative of sine is cosine. Inside stays the same, times the derivative of the inside, which is just 3. So again, if it helps me to color code it, that's where I had the original first. Here is the derivative of the first. And then I had, here's the derivative of that second factor, and then the original of the second factor. So I have done the product rule. You can simplify this one as well. So if I have my second derivative of x, so I have a negative 6 times 3, so that's going to be negative 18 sine squared of 3x plus an 18 cosine squared of 3x. And so that is, again, the second derivative. So again, if you ever see a problem that asks you to find it, you just basically are taking the derivative twice. And it does definitely help to simplify the first before finding the second. Some of you might be looking at that and thinking there's some other ways to do it. There technically are, like technically this f prime you could simplify using a double angle identity. And we can also simplify our final answer using another double angle identity. But for us right now, I just want to make sure that we can do the derivative rules for these problems.
Mr. Brown,
Yes.
if it was like sine 3x and then cosine 2x, would you have to multiply by 3 and then multiply by 2 again after when you're finding the second derivative?
Because I'm visual, say it again what you're asking.
Like if f prime of x was 6 sine 3x and cosine 2x instead of 3x, when you're finding the second derivative, do you have to multiply by 2 and 3 at the end?
So if I was doing this, we can just work it out. Like it's a quick one. So if I wanted to find the second derivative of this one, so I have the first times the derivative of the second, so that'll be negative sine of 2x times the derivative of 2x, which is 2, plus, and then I have the second times the derivative of the first, so the 6 comes across, sine of 3x, the derivative of 3x is 3. So you are multiplying both by 2 and the 3 from the chain rule, but like not at the same time.
Oh.
So it's just multiplying by 2 when I took the derivative of the 1 with 2x, and times the 3 when I multiplied by the 1 that had the 3x inside of it.
Wouldn't that sine turn into a cosine?
Yeah, that sine would definitely be a cosine. So that's actually where I'm going to like stop my notes for today. I did want to give you time to work on homework or ask questions if you have them. I guess I didn't give you too much time, but you do have some time to work on it. Your homework, again, if you're looking at it, so you can do all of homework 5. I also do want to say that you can start homework 7. Like there's actually nothing new I need to teach you to do homework 7 if you're looking to get ahead. Homework 7 actually looks a lot like the warm-up that we did. Monday, we're talking about the derivatives of exponents and logs. It's going to be 4 more rules to learn. I do know I will start having students coming in next week. If you were concerned about how full the room is going to be, this is the maximum I'll have each day. On Monday, there'll be a maximum of 5 students in my room. On Tuesday, a maximum of 4. Thursday, a maximum of 3. And then Friday, a maximum of 6. Wednesdays, are asynchronous. So this first Wednesday lands on a review day. So we will not meet officially for class. It will kind of be like office hours all day long. And things you'll be doing on Wednesday is, of course, finishing your homework and working on your briefcase binder, which does bring me to, I did share it with you, I think it was yesterday. It's shared with you either way whenever I shared it, but on your briefcase binder, I did go ahead and share with you the Unit 2 stuff. So you have your quick reference. You can fill out all of it now except for these log rules that we have. The unit summary I posted, so you can start that. I've posted the review questions, which there are 7 of them. And then you can also begin your quiz corrections as well. So any of those you can do to kind of get ahead. Monday will be notes, Tuesday will be notes, and then Wednesday and Thursday are going to be review days. So with that being said, I do hope everyone has a great weekend and get some rest. And I will see you